Now let's look at MOs when you have a transition metal and the ligands that are potential pi donors. In other words, they have lone pairs on them. So we're not going to really think about any orbitals except for the T2Gs, because they would be, for instance, dxy, dyz, dxc. They have the right symmetry to interact with orbitals, right? Like p orbital on the ligand. So if you think about it, we have 3 of these T2Gs, so that means we're going to have 3, let's say, p orbitals, maybe with lone pairs. And so here are those lone pairs right here in these orbitals. And so what we're going to do, if there's going to be this pi donation with these T2Gs, what we're going to do is combine these orbitals, make new MOs. And here they are. We can put the lone pairs from the p orbital into these lower ones, and then we have, these would be the upper level orbital. And now you see the delta, the transition for an electron, let's say a d electron that was populated in this T2G, now it's finding itself here. To move it to the EG, the delta would be smaller than in the previous case when we just had sigma donors as the ligands. So ligands like fluoride, bromide, hydroxide would be considered weak ligands. They have all multiple pairs. They would engage in pi donation, and again, this delta here is very small, hence they're weak field ligands. Note that, again, these are low-lying occupied p orbitals, or pi orbitals. And if you look, the pi star, the anti-bonding versions of these are very, very high. So these are the ones that are closest in energy with the, in this case, this slightly populated T2G level. So we get the interactions here because they are similar energy. When we talk about pi accepting ligands, we'll see that's going to be slightly different. Now let's look at an octahedral complex that has pi acceptor ligands like carbon monoxide CO. If we look at it here, again, we have the T2G and EG d orbitals on the metal. And so they're separated because they're interacting through the sigma bonds we just talked about. But now we'll look at the ligand orbitals. And again, these pi acceptors typically have multiple bonds, so they're going to have pi electrons, but they're really low. They're going to be really low in energy, and they won't be able to interact with the T2G orbitals that we want. Instead, and this diagram maybe doesn't reflect it beautifully, is that they will interact with the pi star. So those would be like the LUMO on the ligand. So we'll have an interaction between the T2G and the basically pi or p star orbitals on the ligand to produce 3 bonding orbitals and 3 anti-bonding orbitals. So if there was initially an electron in the T2G, now it's down here. It's been stabilized through this interaction. And what's happened is now we have an increased delta over the previous case in which we didn't have any pi acceptor ligands. So this kind of back bonding or pi accepting, what you need essentially is a metal that is pretty rich in electrons, low oxidation state, so it can actually donate an electron to this, and we observe that in this diagram. So this interaction is derived from, let's say, the HOMO of the metal, in which the electron in this case is in a non-bonding orbital, interacting with the LUMO of the ligand to produce this strong interaction. And in this situation now, what's going to happen is that weakens the bond in the ligand, but it essentially promotes a stronger metal ligand bond. This would also be associated with a, like I said, decreased strength of bond between the C and the O, in this case, if that were the ligand. And of course, one could detect that by IR spectroscopy.